In this video, we'll look at some of our special cases of exponents, including an exponent of 0, an exponent of 1, or maybe even no exponent at all. So first, let's explore an exponent of 0 or an exponent of 1, and what your calculator is telling us that's equal to. So we'll start with a small base number like 2. If we wanted to evaluate what that's equal to, we could do 2, that caret key, and 1, and we would see that that's equal to 2. If we do 2 to the 0 power, again, 2 caret 0, we see that that's actually equal to 1, which is probably a surprise to you. So in this video, we're going to look at why is that true. So let's look at a couple more exponents to see if we can figure out what's happening with weird things like 2 to the first, 2 to the 0, or even 2 to the negative 1. If we evaluate each of these, and we'll start with 2 to the third, we see that that's equal to 8. 2 squared, or 2 to the second power, is equal to 4. 2 to the first is equal to 2. Again, that new weird one, 2 to the 0, is actually equal to 1. And then we see that 2 to the negative first is equal to 0.5, which we know is the fraction 1/2. So let's use this table to see if we can figure out what's happening with these weird exponents. You'll notice that as we go down this side of the table, our exponent is dropping by 1 each time. If we think about what that means we're taking away multiplying by 2. So another way of saying that is as we go down this table, we're dividing by 2 because we're taking one of them away. So 8 divided by 2 is 4. 4 divided by 2 is 2. And 2 divided by 2 is 1. So that helps us explain why something to the 0 power is equal to 1. We're essentially dividing it by itself, which equals 1. So first two special cases, we have an exponent of 1 is always equal to the base. So something like 2 to the first is equal to 2, or x to the first would just be equal to x. And an exponent of 0 is equal to 1, always, no matter if you have a numerical base like 2 to the 0, or if you have a variable base like x to the 0. Both of those are going to equal 1. Then the last one would be negative exponents. And maybe before this you were thinking that it would be a negative answer. But we can see if we follow this same pattern, sorry, you can hear my dog in the background, I'm going to take 1 and divide it by 2. Well, 1 divided by 2 is the same thing as 1/2. So that's why any negative exponent is actually going to become a fraction and not a negative number. We're dividing by that base as we work our way down. So 1 divided by whatever base you have is going to give you that fraction. So how we can summarize that is anytime you have a negative exponent, it moves to the denominator and becomes a fraction. So in our example of this table of 2 to the negative first, we saw that was equal to 0.5. Or another way of writing that would be 1 over 2 to the first power, which is 1/2. So if we had 2 to the negative second, again, that negative tells us to move it. So it would become 2 to the second power, and 2 to the second power is 4. So that's the same as 1/4. So notice, as soon as we moved it, it dropped the negative and became positive, right? It was not a negative number. It was actually a positive number, just a fractional form. So if we had something like x to the negative 4th, all we would need to do is make it a fraction with a numerator of 1 and move that to the denominator. And again, that negative then goes away as soon as you move it to its proper location. So a couple of examples to help you with the fact that an exponent of 1 doesn't really make a difference. We kind of use 1 as this like invisible number in math. If we look at these first two, we have an x by itself and then a 1x, so a coefficient of 1. Well, we know that a coefficient of 1 is not really necessary. So these two things are actually the same. There is no difference between them. Same type of thing if you have an exponent of 1. Mathematically, it's really not making a difference, so these two things are the same. So if you ever see something by itself, you can kind of pretend that there is an exponent of 1 there, we just don't need to write it. So sometimes you'll hear this called the identity rule, where anything without an exponent is the same as if it were to have an exponent of 1. So we're going to look at a couple of examples having an exponent of 1 and where you would see an exponent of 0. So again, normally you don't write an exponent of 1, and anything to the first power is just the same as the base without an exponent there. So if we look at this problem, I'm going to kind of split it up. So I have an 8, a coefficient, so no exponent rules there, but there's no other coefficients to work with. So that's going to stay as 8. And then I have dividing with exponents, so I know to subtract those exponents. So that would be the same as h to the 6 minus 5, which is h to the first power. Now that's a totally acceptable answer, but one way to simplify that would just be saying that's all the same as 8h. So here's an example where we get an exponent of 1 and decide to simplify it, clean it up a little bit more, and take it off of our final answer. But again, those two are equivalent or the same. If we look at this next problem, we have two bases happening. So again, I'm going to kind of visually split it up for myself. So with the m base, I would have m to the 4 minus 3. And then with these n's, I see that there's an n by itself down here in the denominator. So what I'm going to do is kind of mentally make a note that that's the same as n to the first power. So I would want to do 8 minus 1. And a lot of times what happens is people forget that that's 1 and would leave it as 8. But remember, that's one end on there that we're taking away. So I would have m to the first power and n to the 7th power. Again, we could write that the same as just m times n to the 7th power. So here we see that identity rule happen twice. One where we have the option of taking this off for our final answer, and the other option where we started without an exponent here on that n and had to remember that's really n to the first power when there is no exponent. Now let's look at a couple of an exponent of 0. Anything to the 0 power is equal to 1. So if we look at this first example, we have 10 times w to the 0 power. Now it's important to note that that 0 is only on the base of w, not actually impacting the 10 at all. So we have the 10, the coefficient, and then that w to the 0 is really the same as 1. So this problem is the same as 10 times 1, which is 10. So the whole thing isn't 1 because that 0 is only on the base of the w. If by comparison we had something like 10 to the w, or 10 times w all to the 0 power, that entire piece would be 1. So you hopefully can see those slight differences between those two problems. If you look at the next one, there's two different bases. So again, I'm going to kind of split them up. I would do a to the 10 minus 5 and b to the 6 minus 6. So a to the 10 minus 5 would give me a to the 5th. b to the 6 minus 6 would give me b to the 0. Just like this last problem, this piece is the same as 1. So a to the 5th times 1 is just a to the 5th. This is a great example to help us see another reason of why something to the 0 power is equal to 1. Here we have b to the 6th over b to the 6th. Anything divided by itself is equal to 1, or we could even expand these out. So that would be 6 b's at the top, 6 b's being multiplied on the bottom, and we could see that each pair would cancel out to 1. So anything over itself is equal to 1, but again, our exponent rules tell us that that's b to the 0. So just another small explanation of why something to the 0 power is 1. You're essentially dividing it by itself.